Hello, everyone, and welcome to our live session for today, September 11th, 2025. We are excited to be here. My name is Matthew. I am one of the course staff who runs our online courses and does the behind the scenes stuff here on the live sessions. And I'm just going to give you a quick overview of how these live sessions work. For those of you who are new to our sessions. And then I will hand this over to Professor Impey, who will give us a topic to kind of think about and possibly spur some questions. And then we'll get started with your questions. So the way this works is please post your questions in the chat. I will grab those from there. Please ask your question only once. We do see all of them. I generally try to go in order, but sometimes we jump around to give more people a chance to have their questions answered, and also to cover a variety of topics. We also have some email questions that come in from people who are either not able to be here or who just prefer to send them via email. So again, if you have a question that you want answered the most, maybe put that first, because I generally take the first question that people ask, and then sometimes if there are enough opportunities, then you'll get a second question answered. But ask your most burning questions first. I think that's it. I'll hit the like and subscribe buttons on our channel. Make sure you hit that thumbs up icon so that these can get out and reach a larger audience. And if you want to join our mailing list, scroll to the top of scroll to up the chat where I have the Google group link, and you can join those there. We also have a Google Calendar you can join, which will tell you about upcoming live sessions. But if you follow our channel, you'll get those notifications. All right, Chris, why don't you say hello to everybody? If you have a kind of an initial discussion topic, then we can get going.
Okay, welcome everyone. There's a very exciting news story recently, also celebrating an anniversary, the 10th anniversary of the LIGO, the Laser Interferometer Gravitational Observatory, which is the gravity wave detector that first discovered merging black holes, a signature predicted by general relativity 10 years ago. And there's been a very recent observation, very exciting, of two large mass black holes colliding and merging, which gave a really strong signal to the LIGO detector. And they were able to use this merger event to prove one of the hypotheses made by Stephen Hawking almost 50 years ago. Stephen Hawking, unfortunately, no longer with us, so he didn't get to see this confirmation. But they actually showed that the surface area of black holes grows as his theory would predict when black holes merge and combine. The masses clearly combine. So in this case, two 30-ish solar mass black holes combined. And the result was not the sum of the two masses. It was the sum of two masses minus about 3 times the mass of the sun that came out in pure gravitational wave energy. So there's a little mass energy conversion there. And then, not because they could directly observe the size of the black holes, they're far too far away for that, and the LIGO is not a telescope that can measure the size of things. But by modeling the waveform of the merger event, they were able to model and constrain the surface area of the black holes that collided, and then the resulting black hole. And the two black holes that collided had a combined surface area of 240,000 square kilometers, and the merger result had a surface area of 400,000 kilometers. And that increase in surface area as the mass of the black hole grew was exactly in accordance with general relativity and Hawking's prediction. So this is a sort of stunning result, actually. There's a big unfortunate shadow hanging over LIGO as it celebrates its 10th anniversary. A sad event of the last few weeks was Rainer Weiss, one of the 3 scientists who won a Nobel Prize for the LIGO project and his discoveries. He's a physicist and an engineer out of MIT. He died. He was, I think, 92 years old, so he had a good run. But that was a sad event in the physics community. And more ominous, the administration's current budget for LIGO proposes shutting down one of the 2 detectors to save money. And this is not a political statement. That's an asinine thing to do because you essentially completely compromise the experiment. LIGO depends on simultaneous detection of the space-time ripples at two distant locations. That's how you distinguish it from geothermal noise or something going on locally. So without the two detectors of LIGO, one in Louisiana and one in Washington State, it can't really function the way it was supposed to. So shutting down one of the two detectors is a silly, just a crazy move because it will kill one of the most great scientific success stories of the last decade. Hopefully that doesn't pass. Congress has shown some sign of having a spine when it comes to some of these science budget cuts, but that will all be decided in the next few months.
All right, thank you very much for that setup. We will hit some questions from our participants. Adrian Murray, who's on with us live, asks, can you please comment on the idea that it is logical that different parts of the universe move or might move at different velocities, as the universe is not one discrete object, but rather composed of many parts?
So, in principle, it is possible that the expansion of the universe is not uniform or isotropic. It's this assumption of cosmology that the universe is uniform and isotropic. That's called the cosmological principle. But we can test this because we can look at the Hubble law, or the relationship between the distance and recession velocity of galaxies in different directions in the sky, and that's been done. And there is no variation. The expansion rate you measure in one region of the sky is the same as another region of the sky. That expansion rate does vary over cosmic time, but not with direction. So there's no direct indication or even indirect indication that the universe is non-uniform in that way. It does seem that the cosmic expansion is one thing across the entire observable universe.
Excellent, thank you. The next question is from one of our live participants. From Supreme Scientist would like to know, can you define pseudoscience and explain why astrology fits this definition, but astronomy doesn't?
Sure. Pseudoscience is a useful term. So it sounds a little obscure, but basically, pseudo means something pretending to be something that it isn't. And pseudoscience is something that pretends to be science or has some of the attributes of science, but isn't truly science in the sense that it's based on evidence, that it can be tested, and it, in principle, can be refuted if it doesn't satisfy the evidence and doesn't have scientific principles behind it. So astronomy is clearly scientific because astronomy is about observing the universe and drawing inferences about what we see in the universe, about its size, its shape, about the mass and energy content, and so on, and how the objects in it behave and evolve. So astronomy is a mature science where it follows the principles of science. Astrology is the idea that the positions of the planets, the sun, the moon, and the planets at the time of your birth somehow affect your life, your outcome, your personality even. And so different star signs have different attributes according to astrology. Astrology is a system that goes back to Roman times and even before. And it is on its face to most scientists nonsensical that, the population of the world will divide into 12 segments with different personalities according to the position of planets when they're born. So there's no physical basis for that at all because planets don't really have an influence on us. They're so far away. The only gravitational effect we feel is from the Earth that we're standing on and indirectly from the moon and, of course, the sun that we orbit. The planets have negligible effect on us. So there's no physical force that could be behind astrology. Also, it can be debunked and has been debunked in many experiments. And 2,000 years of star signs have already caused a problem because the precession of the Earth as it spins on its axis has shifted the constellations relative to the original formulation of astrology over 2,000 years. So star signs have all been shifted by one. So whatever star sign you thought you were, you have to look over to the next star sign. That's the star sign you actually are. So that almost alone is sufficient to debunk the idea. And so astrology seems to be scientific because people cast horoscopes and you can pay a lot of money to a professional astrologer and she or he will run, they often are women, She will run computer programs or software, and it seems very sophisticated. It seems to be based on motions in the sky and science, but it isn't. There's no scientific principle behind it.
The next question is from David, who sent an email. If the accelerating expansion of the universe is due to dark energy, would that not imply a reduction in dark energy due to work being done, which in turn would mean dark energy would be depleted at some point in the future, allowing gravity to be the dominant force in the universe, pulling everything back together?
So that's a sensible supposition based on our normal understanding of energy. So it is true that normally energy is finite. If you put it in space and that space expands, that energy will be diluted or diffused. Dark energy is fundamentally different, so it does not obey those same principles because dark energy appears to be a property of the vacuum. And so in a very strange way, as space-time expands, dark energy continues to be there at the same level. So there's more dark energy essentially being created as space-time expands. So it's not dissipating, it's not diffusing, it's not loosening its strength at all as time goes by. It's constant per unit of expanding space. And that's driving an ever accelerating expansion. And that means the nature of dark energy is fundamentally different from something like kinetic energy or potential energy, the other kinds of physics energies that you might encounter in a textbook or at school. And of course, we don't really understand this form of dark energy. It's perplexing. To a physicist, it has negative pressure, which is a very strange characteristic.
Thank you. The next question is from Adrian, who's on with us live and asks, Professor Impey, how is it that all 92 elements of the periodic table are found on the Earth? The convergence of all the elements in the periodic table into such a tiny volume of our galaxy seems unlikely.
And that's an interesting question. Yes, the elements are produced in different ways. The vast majority produced in stars during their lives or violently at the end of their lives. And they're produced at diverse locations in the universe. So for them all to end up in the Earth is an interesting outcome. However, so part of the answer is that spectroscopy is an incredibly sensitive technique for detecting tiny concentrations of chemical elements. So when we look at the abundance on the Earth or within the solar system, actually, or in the solar neighborhood of elements across the periodic table, it varies by many orders of magnitude. And so an element like gold or platinum is literally billions of times, tens of billions of times rarer than hydrogen or helium, or even carbon and oxygen and nitrogen, the next three most abundant elements. So the reason that they all can be detected on Earth is because we have extraordinary sensitivity. So these rare elements are not detected in any large concentration at all. But the other part of the answer, of course, is that the ingredients made in stars and sped into space are distributed. The university is a sort of big mix master where elements are being thrown into space and then circulated in the interstellar medium. And as the galaxy rotates, the elements wind through interplanetary space and interstellar space. So there's a lot of mixing that goes on. So it's not like an element created in one location that's a rare element will just sit there and stay there. It'll be dispersed, which allows us to detect it.
The next question is from an email. Wendy Traver asks, it's a two-part question. What theory of cosmic evolution do you favor? The one-time occurrence of the Big Bang or a cyclical cosmology, such as Penrose proposes? And what pieces of evidence would you need to convince you that our universe could be the descendant of a previous universe, and that the cyclic cosmology could be correct?
So the conventional cosmology is a Big Bang cosmology where the origin 13.8 billion years ago is the beginning of everything, all space, all time, all mass, all energy. Penrose and others' cyclic cosmologies are fascinating because they're trying to finesse the whole idea of a Big Bang and a singularity at the beginning of the universe, which is a sort of unphysical concept. And they understand that, so they're trying to reach behind the singularity to try and understand possible precursor state. And so there are plausible cyclic cosmologies that have been invented, not just by Penrose, but by others. The question is, are they testable? The question is, what is the observational signature? Because to adopt one of those, you'd have to have a sign, obviously, of the previous cycles of evolution. And that means some information would have to pass through the cycle. And that's a problem because Stephen Hawking actually ruled out the bouncing universe, which was a version in the 1970s and so of cyclic universe, by arguing that the entropy would increase through the Big Bang and the Big Crunch, and essentially information will be destroyed. So the logic of being able to detect a sign of a previous universe when it goes through a sort of entropy creating singularity before it reemerges is a bit of a problem. And I haven't seen any kind of prediction of an observable effect that astronomers could go out and look for to verify this theory.
The next question is from Duplessis Jonathan, who asks, can you please discuss the recent NASA announcement about the life finding on Mars, and specifically the rock with potential traces of life that I think was sort of the potential biosignature on Mars?
Yeah, I haven't read the research paper yet, so I'm going to just say a few limited things. This is part of the agenda of the Perseverance rover, the current and best equipped Mars rover, which is looking at it was demonstrated the habitability of the places that it's exploring around the Gale crater. And as it explores other rocks and does chemical analysis of these rocks, because it has a spectroscope and it can get material off them and see what it's made of, it's found not just sort of chemical hints of a metabolism at work leaving behind waste products, but also morphological features that suggest there could have been microbes operating there. Now, to be very clear, it's not finding fossils. Microbes don't leave fossils. So this is sort of, invisible traces of life based on pure geology and chemistry, without actually seeing the remains of a living creature, however tiny.
Excellent. Thank you very much. The next question is, so that we've actually gotten this question twice, and so Crazy Lazy asks it, and let me see if I can find the other one. I don't see. Oh, and Mabab Raman asks, they'd like to know if it is possible that our universe could be inside of a giant black hole, and the cosmic horizon could be the event horizon of this black hole. What are what's the evidence that could lead to something like that, and how do we know that's not
Right.
true?
So, to put it simply, there's no direct evidence of an exterior event horizon or the fact that the universe is in a black hole. The cosmic horizon that we see, which is the limit to our vision, is caused by the fact that there's a finite volume of space that we can observe given how fast light travels in the universe and the finite age of the universe. So that's the cosmic horizon. That's just a limit to our vision based on how far light could have traveled in the 13.8 billion years the universe has been around. Now, that doesn't imply at all the same thing as an event horizon, because an event horizon in black hole physics is caused by a sort of gravitational situation where the compression of matter is such that a region of space has an escape velocity that's the speed of light or higher. Ergo, nothing can escape that object. The universe does not operate as a single static object in that way because, of course, it's expanding. And so even if you consider all the mass and the energy in the expanding universe, it doesn't fit the formal definition of a black hole. So I think this idea is very interesting and intriguing, but it doesn't really fit with the data on cosmology at this point.
The next question is from Rasta Vibes, who asks, Professor, what role does the philosophy of science play in astronomy, and how is it relevant?
Philosophy of science has a role to play in astronomy because astronomy is a different category of science from a lab science. So we have sciences like biology and chemistry and physics in large part, which can operate in the lab in conditions that can be controlled in situations where you put ingredients in or you set up physical conditions and you watch an experiment happen. The universe is a natural experiment that we have no control over that happens out there that we can only access indirectly through our observations. And that puts fundamental limits on what we can know. And the philosophy of science is a field that's well set up to talk about those limitations to our knowledge and how a field works when it can only be verified by observations, and also when we can't see everything that we might want to see. There are parts of the universe that we know exist physically based on our models, or we're confident they exist, from a Big Bang model, for example, that we can't actually observe with our telescopes. So how do we treat them? What's the epistemological status of regions of space and time that our theories tell us exist but that we can't observe? So those are areas where philosophy of science definitely plays a role in sort of understanding how astronomy is similar in some ways to other sciences, but in some ways quite unique.
Excellent, thank you. The next question is from Hernan Reyes, who sent an email. Dear Professor Impey, recently there have been discussions about the possibility of a spacecraft launched from Earth to intercept an interstellar object such as Oumuamua traveling through the solar system. The question is, with these objects moving at these extraordinary speeds and us not knowing that they're coming, how likely is it that NASA or ESA could muster a mission in time to catch and follow an object like this?
Yes, I've heard speculation about this too. And the simple answer is it's extremely unlikely that they could do this experiment. I mean, some of this is just pure practical constraints of these agencies, ESA and NASA, the European Space Agency, and NASA in the US, having a suitable launch capability available at short notice that can do this. The private sector may be able to step up. Maybe Elon Musk eventually will have starships operating reliably enough that they can leave Earth orbit, since they're destined for Mars, and do this work. But remember, in all the Starship tests so far, no Starship they barely reached Earth orbit, let alone left it. So you need a mature launch capability, and that only exists in the hands of NASA and the European Space Agency, and they don't have a lot of spare capacity. Also, the speed of these rockets in interplanetary space is low. It's not a good prospect to be able to intercept an object like that. And also the lead time is kind of short for the Oumuamua and the other couple of objects that we think might have interstellar properties. Their speeds and trajectories are such that they were picked up kind of late, and so you only have a couple of months notice, and that's just simply not enough time to intercept a very rapidly moving object.
Excellent, thank you very much. The next question is from David Gold, who's on with us live, and asks, how does the conservation of momentum apply to the accelerating expansion of the universe?
Well, the conservation laws of physics do still apply to the universe as a whole, but in the case of the accelerating expansion of the universe, it's definitely a non-standard situation, because the dark energy that's causing the accelerating expansion is a property of space-time itself. And so in physics terms, the equation that is relevant is that the density equals minus P, or minus the pressure. In other words, there's negative pressure operating in terms of the dark energy. So its role in momentum is also strange because of that negative energy aspect. So I don't think you can use the standard conservation of momentum equation when it comes to describing dark energy and its effects.
The next question is from, excuse me, one of our live participants, and Yang asks, I wanted to ask why entropy has not been replaced by a concept like enthalpy in astrophysics and cosmology. You know, can you talk about the differences between entropy and enthalpy, and why we use one over the other?
I mean, enthalpy is an important and sophisticated physics concept, so beyond the level of this course too. So this is sort of a question that's not usually on our landscape for this Q&A session. But entropy, still has a reasonable role to play. So we can talk about and measure and predict the entropy of physical objects like stars, maybe not galaxies, but certainly of stars and combusting objects in the universe. And that expression of them in a standard form of entropy, which would be seen in an undergraduate textbook, still makes sense. So I think entropy still has a role to play in talking about the properties, especially of stars.
The next question is from Echo One. Given the pace of exoplanet discoveries, do you think we'll detect evidence of life beyond Earth in our lifetime?
That depends on how old you are, but I think yes, and I hope for my sake, yes, too. The exoplanet discovery rate has slowed down. It was at its peak when Kepler was operating, and soon after, as Kepler found probably half of the 7,000 exoplanets that are confirmed. The next stage of life detection and scrutiny of the best of these exoplanets, the closest to the Earth and the closest to Earth size, that's a more difficult experiment. So that the rate of discovery, if you like, is definitely going to slow down in this next phase of the research. But it's got a much more ambitious and interesting goal, which is the actual detection of life beyond Earth. And I do think that will happen within 5 to 7 years.
The next question is from Pecornin, who asks, why does a neutron star not reflect light? And if a star came close enough, would we not be able to see it?
So a neutron star is indeed a solid object. It's made of pure neutron material, so it's essentially a very large atomic nucleus. And so you might ask, what does a neutron star look like if you could see it? A neutron star also has incredibly intense gravity. It's just one step below a black hole in terms of the intensity of the gravitational force. So it's not clear that if light hit a neutron star, it wouldn't all get absorbed. Much of it will get absorbed, but some of it would escape. And I don't even think we can say what color a neutron star would have. The size also is very small. Neutron stars of dead stars is slightly larger than the sun, or a couple times larger than the sun. Is about 10 kilometers, the size of a small town. So these are far too small objects to actually resolve, to see a picture of, and that's why we don't actually know what neutron stars look like, because you can't take a picture of something that small that's probably trillions of miles away.
The next question is from Arif Roni, who asks, what is vacuum decay and false vacuum?
So the idea of false vacuum and vacuum decay, they come out of inflationary cosmology. They come out of the idea that the universe started in a very tiny state, obviously the Big Bang, which is a singularity, but that around the time of inflation, which is a process we think happened about 10 to the minus 35 seconds after the Big Bang, a field called the inflaton field, so it's a field specific to inflation. The fundamental nature of it is unclear because inflation has not been confirmed. That field seeded the exponential expansion of space-time. And in a sense, the space-time that led to our universe, it was a false vacuum because it was false in the sense that there was energy that could be borrowed from that vacuum to cause the expansion of space-time. Pure vacuum that's not doing anything, has no energy in it, no potential energy in it, is boring and won't accelerate any expansion. So in that sense, it's a false vacuum. And then the idea of the vacuum decay is the possibility that these energy states that led to something like inflation are not stable, but they can decay over time. It's also an issue of the modern universe because if vacuum energy, the thing we think causes the accelerating expansion of the universe, if that fundamental quantity does decay in strength, then the accelerating expansion could terminate and the universe might start to recollapse. That's pure speculation, though.
The next question is from one of our live participants, or sorry, from an email. What would a universe without isotopes be like?
So isotopes are versions of chemical elements with different numbers of neutrons. So the number of protons in an atomic nucleus defines the chemical element. So for an object with a proton, that's hydrogen. With 6 protons, that's carbon. And 8 protons, that's oxygen, and so on. And typically the number of protons and neutrons is equal for the lower numbers in the periodic table, and then it becomes unequal. But in addition to the element where there's equal numbers of protons and neutrons, there can be isotopes. And the isotope is just a version of the element that has an extra neutron, or maybe 2 extra neutrons. And so there can be multiple isotopes for different elements. Carbon's a good example because carbon has atomic number of 6, and stable carbon has 6 neutrons, 6 protons, and the mass is 12. But there are 2 isotopes of carbon, carbon 13 and carbon 14, one with 1 extra neutron, one with 2 extra neutrons. Carbon 13 is extremely rare and highly unstable, and carbon 14 is also radioactive and unstable, but very interesting because the half-life is 5,700 years, and that's what lets us use the amount of carbon 14 that living creatures ingest along with the stable and dominant carbon 12 and that will decay when the living creature dies and stops ingesting air and having a metabolism. The decay of that carbon 14 gives you the age of that formerly living creature. So you can use it to date bones or living creatures, over ages of tens of thousands of years. So isotopes can be extremely useful. And so almost all the elements going up the periodic table, except a few with very low atomic numbers, have isotopes, multiple isotopes.
The next question is from Faisal. 3 interstellar objects that have visited the solar system in the last few years that have been detected. Is this because of an improvement in observation, an indication of some cosmic event close to our solar system, or purely coincidence?
I think it's improvement in observation. There's nothing going on suspiciously in the universe that would lead to more interlopers from outside the solar system. But our ability to detect them has improved. And that's because there's a set of telescopes, including arrays of telescopes and networks of telescopes, that are doing pretty systematic all-sky surveys. And so they're perfectly positioned to catch these objects. Now, many of these telescopes are looking not for interstellar interlopers like Oumuamua, but they're looking for near-Earth objects that might collide with the Earth. So they're trying to protect us by making a catalog of near-Earth asteroids and Earth-crossing asteroids and comets that might come close to the Earth. So these networks of telescopes have got better and more sophisticated, and I think that's leading us to pick up more of these interstellar interlopers.
Excellent. Thank you very much. The next question is from one of our live participants, and Natalia asks, so regarding this Martian biosignature, I think what they want to know is, will it be analyzed on Earth? Like, I think they want to know if it will be brought back. But if not, can you talk a little bit about how we analyze these kinds of this kind of information from our Martian
Right.
friends?
This sample will not be brought back to Earth. So Perseverance has for a couple of years now been caching or storing samples in small vials that are sealed for eventual return to Earth by a planned and hoped for sample return mission. And it's pretty much finished that work. I think it's almost 3 dozen vials have been created, and those vials have been laid down on the Martian soil to be picked up by another rover, or they're sort of being sent there. Most of them are being stored at what we might call a depot for an eventual lander to bring them back home. There was no way for this recent discovery to end up in one of those vials, no way to get it into the vial, and I think all the vials have been filled at this point. And the return capacity can only bring so many back. So this sample is not going to come back to the Earth. It'll just be analyzed remotely based on the spectroscopic signatures and the inference that can be drawn from them, which is unfortunate, but that's the way it goes. That's why at some point we need more than one sample return mission. The one we have is incredibly complicated, expensive, and may not even happen.
The next question is from a live participant. Sunlight asks, how close are we to understanding what happened during the first fraction of a second after the Big Bang?
I think we've got some good progress. We've made progress already. There's physics from the early part of the Big Bang that we can understand. So we think we understand how we certainly understand the creation of elements. That's in the first few minutes. And if we're talking about microseconds, we also think we understand how particles and antiparticles were created from pure energy, and then eventually, due to a slight asymmetry in the forces of nature, the particles collided and annihilated with the antiparticles, leaving behind a lot of energy and a small residue of particles. So that's physics of the first microsecond that we pretty much understand. And thereafter, it gets more difficult. I think thereafter, the big threshold is back to the era when the inflationary model applies. And there's indirect evidence of inflation, which is probing very tiny fraction of a second after the Big Bang. But that is not definitive evidence. So I think our ability to diagnose earlier than a microsecond is fairly limited.
The next question is from It's a Literary Life, who's on with us live, who asks, if we discovered a truly Earth-like exoplanet tomorrow with undeniable signs of life, how would that change the priorities of astronomy research over the next decade?
It's a good question. So the first life detection, we imagine it happens on an exo-Earth, an Earth-like exoplanet. What would that change? Well, it means we would bear down on this exoplanet with all the tools of the astronomy community, relentlessly and without ceasing. We would obviously have to use every new facility of larger capacity. So, however this planet was discovered, we're still waiting the first light on some very large telescopes under construction, three of them, two in Chile and one in Mauna Kea. And those telescopes would be deployed onto this new object for sure. Now, as far as doing better than that, that's going to be a little hard because odds are that the nearest exoplanets might be in the Proxima Centauri system, but very likely the first exoplanet with life detected on it will be a nearby target selected from Kepler that's Earth-like, but it's going to be tens of light years away, maybe hundreds of light years. So that's thousands of trillions of miles. So there's no way we could send spacecraft there. We'd have to accelerate them to a significant fraction of the speed of light. That's technology we don't have. So we'd still be remote sensing the new exoplanet. But I think we have some very powerful telescopes coming up that would be brought to bear on that.
The next question is from Hernan Reyes, and this is a follow-up to his earlier question about, a mission to intercept one of these interstellar objects. And his question is that there are some scientists like Alan Stern who seem eager to push for one of these kinds of missions. And, in your opinion, what would we expect to learn from such a fleeting encounter with one of these objects? And would it be worth it? Would we learn enough from doing something like this to justify the expense and effort?
That's a hard thing to decide. I mean, measuring, being able to physically measure, possibly even sample, make a rendezvous and sample an object from outside the solar system would be very exciting. I think the motivation to do it, even if difficult and expensive, is that it will be a direct way to measure the chemistry, the chemical composition, and abundance of elements in non-solar system material, which it's very hard to do. We do it indirectly with spectroscopy of gas between stars and gas in galaxies elsewhere and so on. But to have rock, a physical object that we could perhaps sample and bring back samples through a rendezvous, that would be very exciting. That would be the first physical sample of anything from beyond the solar system. And if you could do that, that would be, I think, worth the expense and the difficulty.
The next question is from Arif Roni, who asks, if Moore's law, so the law stating that every year we will exponentially increase the capacity of our microchips, is applied to the LIGO project, do you think it's possible to invent more extraordinarily, um, or sorry, to detect more extraordinarily violent cosmological effects by upgrading the LIGO project?
So the LIGO project, pushes electronics to its limit. But in terms of Moore's law, which really relates to the speed and the capacity of microprocessors on a silicon chip, that Moore's law has continued to hold and make computers increasingly powerful. LIGO itself, certainly the computation required to reduce and understand LIGO data doesn't push computing to its limits, so that does not depend on Moore's law. The question of whether Moore's law affects the way LIGO detectors work also is not, it's not helping with LIGO detectors particularly, because LIGO detectors are not, again, not pushing the envelope of the density of microprocessors. The fundamental limitations on LIGO detectors are shot noise, which is essentially a sort of unavoidable noise associated with the temperature of a detector and the implication it causes on the motion of the electrons in the substrate. And there's nothing you can do about that. Moore's law is not going to help you with that. So in a sense, Moore's law is not going to help LIGO become a better instrument.
The next question is from Emerald Bones Gaming, who asks, how are astronomers approaching looking for life outside of Earth?
Well, the primary method now that people are exploring is looking for an Earth-like or super-Earth planet close to the Earth, maybe a little more massive because that's easier to detect, and using spectroscopy to sniff, if you like, the atmosphere of the exoplanet and look for a metabolism, look for something like what happened on the Earth, where 3 billion years ago, microbes, cyanobacteria, started generating the oxygen that we breathe, and that oxygen has risen over time. So oxygen in the Earth's atmosphere, 18% or 1 part in 5 roughly, it's a telltale for life, and that's the logic we would use elsewhere. It's not the only telltale for life. There are others, but that's a big one. And on the Earth, it's obviously the big one. Ozone is also a telltale. It's a cousin of oxygen and has very strong spectral signatures in the infrared. So those are the tools that astronomers are going to use to look for planetary atmosphere that's been globally altered by microbial life. So it's a well understood method. It's very challenging technically, but the new telescopes that will be coming online soon are going to be able to do that experiment.
The next question is from Aylin, who asks kind of a general question. I can see there being two ways of approaching this. So the general question is, what do you think about the implementation of quantum technology in astronomy? And I can imagine that that question could mean we could talk about how is quantum mechanics used in astronomy, but also how do upcoming technologies like quantum computing factor into astronomy?
Right. So astronomy relies on quantum techniques because astronomy relies on solid state detectors that are governed by quantum mechanics, and their behavior is governed by quantum principles. And since they push those detectors in astronomy to the limit of their capacity and sensitivity, you have to understand the quantum properties of your detectors extremely well. Many of these detectors are operating at very low temperatures to keep the thermal noise down, and that changes their quantum properties. So once again, you have to understand them. So that's a major area, quantum detector physics, if you like. The other one, quantum computing, is definitely relevant because astronomy is dealing with huge data sets now. The current and upcoming surveys, like with the Vera Rubin Observatory, are going to generate many petabytes worth of data. And that has to be reduced and distilled into objects and catalogs and discoveries, hopefully. And that requires enormous computing power. So quantum computing, which is of course still in its infancy, will be adopted immediately by astronomers to deal with the fire hose worth of data they're suffering from with these large new surveys.
The next question is from an email. Don Town asks, now that we're able to detect gravity waves, what is the impact, or what would the impact be of a black hole standing in the path of a gravity wave generated by something behind it? Would we expect the ripples in space-time to wrap around the black hole, or to create a shadow? I mean, what are the effects of
Mhm.
gravity waves interacting with a massive object kind of in the way?
Yeah, that's a very good question. And I think people have thought about this and they've tried to simulate and model it. I mean, LIGO has to operate from a deep understanding of gravitational physics because the binary black hole signatures that were first found 10 years ago have a very particular characteristic. So you need general relativity to solve the equations of what happens when two black holes collide. If you have a background signal of gravity waves, say there was a in spiral of two black holes creating gravity waves that pass through the universe, the question of what happens when they encounter a black hole along the line of sight is an important and interesting one. And yes, because of the ability for black holes to bend space, they will imprint an extra curvature on the ripples that pass through. I don't think it acts as simply as just a focusing mechanism, so it's not like gravitational lensing directly, where mass bends light traveling through the universe, because gravity waves do not operate like light. They propagate it in a fundamentally different way. But yes, there would be an interaction between the highly distorted space-time of the black hole and the waves that sweep over it from a background collision. I've read only one paper where I think people tried to model this. So it's quite a subtle effect, and also the odds of that happening are also quite low. The odds of a background black hole merger having an intervening black hole exactly aligned actually turn out to be incredibly small. So this possibly is a vanishingly improbable event.
So I'm not sure if this is referencing some recent experiments about slowing light. But Cornyn asks a question: if it is possible for light to slow down, or for us to slow light down, is it then theoretically possible to make light stand still or to freeze time?
Yeah, so sometimes people talk a little casually or colloquial about light slowing down in experimental physics. Now, there are experiments where the effect of light speed can be modulated by essentially creating a cavity and creating standing waves. So you can set up a situation where sort of phase velocity of light, which is the speed through which it carries information, is substantially slower than light speed. Though it's a kind of a trick because you're not actually formally reducing the speed of light, which is a fundamental constant. Uh, can you reduce the phase velocity of a light signal to zero in principle in these cavity experiments? Possibly. It's a major goal. Reducing the speed in this way in an experiment allows you to do some interesting experiments. But it doesn't actually or technically mean that you've slowed down time or you can cause time to stop, because time is operating in its own context in space, and is sort of independent of electromagnetic radiation.
The next question is from It's a Literary Life, who asks, do you believe that infinity really exists in space? Is this just a concept, or are there real infinities?
Well, the idea that the universe could be infinite, that space could be infinite, is certainly a viable concept because we'd have to have a reason to refute it. We'd have to have a reason to put a finite limit on the universe. And we have an observational limit on the universe, which is our horizon, which is the size of the universe we can see given how far light could travel in 13.8 billion years. But we don't think that's the edge of the physical universe. And the cosmology itself does not, because especially of inflation, where our entire universe was from one exponentially expanding patch of space-time in a pre-existing medium, we have no reason to put a limit on the universe physically as opposed to observationally. So it's entirely possible that the physical universe is infinite. What does that mean? Well, it's not a meaningful concept because infinities in physics are all not very meaningful, because they represent a quantity that's mathematically blowing up and means you don't understand it. So I think we have to put an asterisk by the infinity attached to the size of the universe because we have no way of verifying that it really is infinite.
The next question is from Nick Fuller. Um, Regarding LIGO, would it be possible to sooner or later observe an effect of the merger of galaxies or other objects in the vicinity?
So LIGO is tuned and is extremely capable at detecting the mergers of black holes, which have masses of from a few times the mass of the sun up to dozens of times the mass of the sun. This recent equal mass merger that was seen was black holes of about 32, 34 solar masses, which is unusually heavy for a dead star black hole. And these frequencies and the gravitational waves that result have signatures in the range of a few hertz up to a few hundred hertz. That's the frequency of the space-time ripples. Well, the frequency of space-time ripples scales with mass. So if you want to actually look at, say, the mergers of supermassive black holes in galaxies, you're now talking about black holes that have 10 or hundreds of times, hundreds of millions of times the mass of stellar mass black holes. And so the time scales of their gravity wave ripples would be similar factor longer than a few hertz or 100 hertz. That's a few hundred times per second. And what that turns into is you get one space-time ripple maybe in a decade or a century. So extraordinarily slow gravity waves. And to do that experiment, it's not impossible, you have to go into space and have a space-based interferometer. And so the LISA project, that's the acronym LISA, Laser Antenna Space Interferometer, is designed, it's a European project with some American participation. It's designed to have three free-floating spacecraft operating as an interferometer and detecting gravity waves from massive objects like galaxies.
Um, we have another kind of conceptual question. Emerald Bones asks, how can something be less than zero, like the negatives? Can you talk about whether negatives are, these, negative numbers or negative quantities show up in nature? Are these concepts? How does that work?
Um, in the math of that goes with physics, you can have negative quantities. Negative mass is not necessarily a meaningful quantity, but in the solution of a Schrodinger equation, you have the square root of a negative number and the square root of a positive number. And the propagation of one of those, the positive number, which is a real number, is determined to be matter, and the square root of the negative number, which is an imaginary number, is determined to be antimatter. So the Schrodinger equation has not just a negative number, but an imaginary number in the math that represents something in the real universe, antimatter. And so it is also possible to have negative quantities. You can have energy in a positive sense or a negative sense. Potential energy is often defined with a negative quantity compared to other forms of energy. So negative physical quantities are not necessarily unmeaningful. They can be meaningful. You just have to work out what the observational properties are for them.
The next question is from an email. One of our participants asks, is it thought that temperature changes in the cooling cosmos were instrumental in freezing out the four fundamental forces?
Yes, the idea of a super force at the origin of the universe, at the singularity of the Big Bang, which then and then as the universe expands and cools, the four forces freeze out at different times as individual distinct forces. That's a well understood concept in theoretical physics. And we have evidence that that happened because we've already diagnosed with accelerators the electroweak force, which is the merger at very high temperatures of the electromagnetic force and the weak nuclear force, two of those forces of nature. So we know that this merger can happen and that it's a function of temperature because you can recreate the temperature of that merger of two forces in the Large Hadron Collider. So it's a pretty well understood concept in physics.
I think you're maybe not uniquely qualified to answer this question, but you're certainly Um, Highly qualified. Arif Roni would like to know, big crunch, big rip, heat death. What do you think is the most probable end of the universe?
Well, the ever expanding universe driven by dark energy is a sort of a version of heat death, even though the universe, ironically, expands and becomes colder and colder. When physicists talk about heat death, they're talking about heat in a very colloquial sense. They're essentially meaning that heat, which is a form of disorder, which is high entropy, that the universe will go into a high entropy state. Entropy will increase, increasing disorder. So, in this ever expanding universe, where everything is more and more diffuse, normal matter will probably decay. Structures will be lost. Any structures that exist will just evaporate, like solar systems and galaxies and the stars that are within them. And so that's what the scenario is of an endless universe where dark energy continues to drive it to larger and larger scales.
And a follow-up is, what data do we need to figure out what would happen? Would it be more knowledge of dark matter and energy that would affect those outcomes?
Yes, I mean, the biggest uncertainty in the future scenarios for the universe is the nature of dark energy itself. Is it constant over space and over time? Um, Telescopes that we're using now, the Vera Rubin Observatory in particular, are going to probably answer the question of whether dark energy varies across space in different directions. You know, is the strength of this dark energy that's causing acceleration varying in direction of the sky and so on? That it will answer that question. The question of whether the dark energy is varying over time is very important because in some models of dark energy, given that we don't know what it is, the dark energy does decay, and that becomes one of the possible scenarios of the future of the universe, that the dark energy decays with time, and that will clearly affect the infinite expansion and may actually mean that it doesn't happen.
Excellent, thank you. I think we have time for one final question for today's live stream, and that comes from an email regarding interstellar technosignatures. So the signs of technology or technological life beyond our solar system. An article I read said that one such indication could be different spectra. Can you talk about what is meant by this?
Well, the same, I don't know all that is implied by that, but one thing that it could be referring to is the same experiments that are being done to detect biosignatures on Earth like planets. That's looking for oxygen, ozone, maybe methane, water vapor as signs of life. They can also, those experiments of spectroscopy in the atmosphere of a Earth like planet can detect tracers that imply technology on the planet, not just microbial life. Nitrous oxide is the best example. That's a gas that is present in the current Earth's atmosphere as a byproduct of industrial activity, but it actually peaked and there was a lot of nitrous oxide, which is essentially pollution, in our atmosphere through the Industrial Revolution. And so and it does not occur naturally. You cannot generate substantial amounts of nitrous oxide by geological means. So if you see an exoplanet with NO in its atmosphere, then there's a good argument to be made that you're looking at an industrial civilization on its way to presumably becoming cleaner and not producing that contaminant because it is a pollutant basically. And there are other possible pollutants that you could look for to indicate a civilization that's using energy and producing waste products. That's an interesting question to finish with, and appreciate the range as always. Our next one is on the books, but I don't remember for when. But we'll be back with you in a week or so.
Excellent. Thank you very much, Chris. For those of you who are still watching, if you all could hit the thumbs up button, that would be great. It helps us spread the word about these live sessions. The next live session will be September 24th. And so we will be back then in a couple of weeks and we will answer more of your questions. So put that on your calendar or again, subscribe to our mailing list. If you haven't checked out our courses, we have 3 of them. The most recent course being the History and Philosophy of Astronomy course. So make sure you go check that out. Thank you again for joining us. We'll talk to you again soon.